Welcome back and to our final lecture of this course. Today we're going to be discussing LLMOps and special tooling we can use to productionize LLM-based systems. Let's start by looking at how LLMs operate in production environments. LLM system architectures can vary significantly across different clouds and environments. This is because we're just starting to coalesce LLM ops design patterns. That said, there are some key system components that will likely always be present in our current LLM system architectures. LLMs on their own are limited in their capabilities. We build systems to augment the LLM's generative text capabilities by integrating additional components into the architecture that can build on the context provided to the LLM or provide guardrails against prompt injection attacks or preventing unintended output. It's common to give the LLM access to internal or proprietary data and/or public data, which provides the external data sources for the context enrichment. We'll also have data processing pipelines that convert this proprietary or public data to vectors, which we then store in an embedding store, usually a vector database. Our LLM itself will be served in our architecture either on dedicated infrastructure or via serverless inferencing, which we'll cover in just a few slides. In addition to the LLM, we may have several services or functions that conduct fine-tuning on the foundation model. Context-specific LLMs are smaller models that are used for guardrails, such as detecting inappropriate content either in the user input or in the model output. Beyond the internal working and functionality of our LLM system, we also incorporate version control for our models, as we've discussed in previous lectures. Model caching is a technique that can reduce latency for our users by preserving earlier outputs. For example, we can cache any results returned by an earlier RAG search so that we don't duplicate that search on every new user input from the same session. Monitoring and observability in LLM systems have unique considerations on top of traditional ML monitoring, especially in agentic systems. The development process for LLM applications is not too dissimilar from other kinds of ML applications. We start with a model, test and evaluate it, iterate on it until we are happy with the results, and then move it into production. In LLM systems, we typically start with an existing third-party or open source foundation model. We then conduct prompt engineering to determine if our model is capable of producing acceptable results without needing fine-tuning. If we aren't able to achieve the desired results using only prompt engineering or other non-fine-tuning based techniques like RAG, then we will fine-tune the model with the assistance of specialized teams and labeled data. Once we're happy with the model's output, we deploy the model into production. We can then use the same deployment patterns we've seen earlier in this class, like A/B testing, canary releases, and blue-green deployments. Let's discuss how we go about serving our large language models. Serving an LLM refers to deploying and running an LLM so it can receive requests and generate responses, basically making the model available for actual use. In order to serve an LLM in a production system, we need to first prepare the infrastructure to run it. This includes loading the model into memory and keeping it running to handle incoming requests. This may seem trivial after all of the infrastructure examples we've worked through in this course, but LLMs often have significant GPU, CPU, and memory requirements. Managing infrastructure for LLM systems is not a trivial task. Luckily, cloud service providers are at the point in their cloud-native offerings where they've dramatically reduced the complexity of hosting LLMs. Next, we need to create an interface where applications or users can send prompts and receive responses. This is usually done by exposing an API endpoint that can communicate via HTTP requests. Part of serving our models include request handling. Request handling is the process of managing the queue of incoming requests, batching them efficiently, and returning responses. Lastly, we need to implement inference optimization techniques to make responses faster and more cost-effective. Serving LLMs comes with some unique challenges. LLMs can be difficult to work with, mostly because they're large and have massive memory requirements. Their size means that they can take a long time to download, load into memory, and deploy. Their size means that we often need to run them on expensive infrastructure. VMs with the memory, disk, GPU, and CPU capacity to run LLMs can cost hundreds and even thousands of dollars per month. Managing the costs and risks associated with the LLMs is critical for the success of any project utilizing them. In the last lecture, we discussed techniques to make models as small as we can so that they are easier to work with. Quantization and knowledge distillation are particularly useful. Quantization has the added benefit that it can be done after training without fine-tuning. LLMs also have unique inference patterns. The output is token by token generation, rather than a score or a classification decision. Observing the outputs of LLMs and determining how well they're performing is a complex endeavor. There are several popular inference frameworks that handle memory management and compute resource distribution for inferencing for us. These are extremely helpful. They let us focus on application logic rather than low-level infrastructure concerns. For example, VLLM is a serving framework that's optimized for high throughput by using paged attention. VLLM has 24x higher throughput than other serving solutions. Text Generation Inference, or TGI, is a serving framework offered by Hugging Face. NVIDIA offers the TensorRT LLM framework. There are tools that are optimized for different environments and at different scales. For example, RayServe is a serving framework that's optimized for distributed deployments, while Ollama is a user-friendly local serving solution. The frameworks we discussed in the previous slide are designed for server-based inference. Think of this like an IaaS model for LLM inferencing. With server-based inference, we have granular controls over the models we use, optimization techniques, and hardware configuration. Server-based inference is ideal for specialized models with unique dependencies, or when you need guaranteed performance with predictable costs. Server-based inference is the best choice for computationally intensive applications, like real-time audio generation or high-resolution image creation with specialized hardware acceleration. Anything that requires custom CPU configuration or fine-tuned environments should use an IaaS server-based inference approach, where the inference service can be optimized effectively on dedicated infrastructure, and where latency and throughput can be precisely controlled. Another use case for server-based inference is for teams with specific compliance requirements or consistent high-volume workloads. For those teams, although the upfront cost of specialized dedicated VMs is high, they may find that server-based inference is economical in the long run. We have other options for inference other than running our own IaaS infrastructure with LLM inference frameworks installed. Another approach we can use is serverless inference. In serverless inference, a cloud service provider maintains the underlying infrastructure for your LLM in a PaaS service model. Serverless inference excels in scenarios with variable or unpredictable traffic patterns. It helps us avoid paying for idle capacity and resource wasting. Serverless inferencing is a good option when the importance of development speed outweighs the need for customization. The operational simplicity of using serverless inferencing lowers the barrier to entry for AI adoption, which makes it a good option for startups, rapid prototyping, and organizations without dedicated MLOps teams. To have a successful serverless inference experience, there's some best practices to follow. First, choose a model that's optimized for your task and a runtime that meets your performance needs. Using smaller, less complex models can reduce inference time and costs for simpler tasks. Next, you can minimize cold starts to improve latency. One way to do that is to configure a minimum number of instances or concurrency so that at least one worker is always warm. Make sure to take advantage of your cloud platform's autoscaling offerings so that your inference service has the available resources it needs when demand spikes. And lastly, always remember to monitor your inference performance and logs. At a minimum, you want to track latency, throughput, and error rates. Some cloud serverless inference services will also expose model invocation counts and token consumption. When deciding between serverless inference and server-based inference, a few key differentiators will help you choose your implementation approach. These are common for any IaaS versus PaaS determinations. First, consider if you have the staff and talent necessary for an IaaS approach. If not, take advantage of cloud-native PaaS primitives to simplify your operations. Next, consider the requirements for your application. Do you have consistent workloads and compliance requirements that you need to meet? If so, a server-based inference service may be the best option. If you have variable traffic and need to develop and deploy a solution quickly, then serverless inference will likely be your best option. Here's some general guidance. Don't build inference infrastructure from scratch unless you're serving simple models in a restricted environment. Many specialized tools are available for LLM inferencing that provide scaling capabilities, centralized auditing and logging, agent step tracking and observability, hyperparameter tuning records, and prompt engineering script management. Now let's explore Kubeflow, which brings machine learning capabilities natively to Kubernetes. Kubeflow is a massive ecosystem for running machine learning workflows natively on Kubernetes. It's an open source project graduated by the CNCF with an extensive community-driven contributor base. Kubeflow can be deployed anywhere you run Kubernetes, whether in a public cloud or private cloud. There are tutorials and examples with end-to-end walkthroughs for AWS EKS, GCP GKE, and Azure AKS in the Kubeflow documentation. Kubeflow has features that map to every part of the ML lifecycle. There are integrations that allow you to run training processes within your Kubernetes cluster using the programming tools you already use. For example, PyTorch, Hugging Face, TensorFlow, and scikit-learn. Kubeflow pipelines provide community-supported ML workflow orchestration, and Kubeflow notebooks provide integrated Jupyter and RStudio notebooks that can be connected to your cluster directly. The central dashboard UI provides interfaces that can simplify your Kubeflow deployment management and help you monitor the state of your ML jobs. Kubeflow also comes with a model registry built in, so you can take advantage of persisting model artifacts even when they're running in a distributed Kubernetes environment. And model serving through Kserve provides autoscaling inference endpoints across clusters. We can see how Kubeflow has components and features that map to each part of the ML lifecycle. There are data preparation pipelines implemented via the Spark operator, notebooks and testing environments that plug directly into the model registry, feature stores that provide offline and online features, and a serving endpoint that makes the model available for calling applications or users. A few Kubeflow add-ons that are worth calling out include Feast, which is an open source feature store, and Elira, which is a JupyterLab extension designed to reduce model development lifecycle complexities. Elira provides a visual pipeline editor that lets you build ML processing pipelines that can be executed with Kubeflow pipelines. Agents interact directly with enterprise systems. They can retrieve data, call APIs, trigger workflows, and execute transactions. AI practitioners and researchers have articulated a few design patterns that empower agents to implement these kinds of tasks strategically and with varying degrees of autonomy. Let's explore these emerging design patterns now. The reflection design pattern provides an agent with an instruction to reflect on, assess, and improve its output. Reflection lets agents catch errors and iterate for quality without always depending on humans. Self-checks and review loops can autocorrect missing details, double-check calculations, or ensure messages meet standards. The planning pattern is when an agent breaks high-level goals into actionable tasks, tracking progress and adapting as requirements shift. Planning combines tool use and reflection. Plans can be generated dynamically by an LLM or follow a predefined sequence, whichever fits the need of the application and developer. Multi-agent patterns are emerging as one of the most promising approaches for implementing practical AI systems. When we talk about efficiently using multiple agents, we often discuss agent orchestration, or the ability for agents to work together to reach a goal. Orchestration patterns can be LLM-driven or they can be deterministic. Some common orchestration patterns include sequential orchestration, where agents are invoked step by step, concurrent orchestration, where agents run in parallel and merge their results, group chat or maker-checker orchestration, where agents debate and validate outputs together, dynamic handoff, where agents hand off their outputs to one another for real-time triaging or routing, and magentic orchestration, where a manager agent coordinates all of the subtasks in a plan until completion. Arguably the most popular agentic pattern right now is React, short for reason and act. The React pattern implements a cycle of reasoning, followed by action execution. In response to user input, an LLM analyzes the current state of the system, including the task and any previous observations. Then, an agent executes an action, usually by using a tool, based on the reasoning. The agent collects the result of the action and passes it to an LLM. This repeats in a cycle until a final answer is reached. The React pattern enables agents to solve problems in real time. React agents alternate between reasoning and action in a loop until the goal is achieved. Here's the overall flow of the React pattern. It starts with a user query, which is the initial input to the agent. The agent then provides a prompt to the model requesting the next steps. The model responds with either the next step or a choice of steps. Next comes the thought phase, which is the model's reasoning output and can be used in business logic. Then there's the action phase, which is the actual decision on the next steps, such as generate a chain of thought output or query an external database. If the action is to use a tool, the model will provide the inputs required to give to the tool. This is followed by observation, which is the result of the action taken. If the task is accomplished, we exit the loop. If not, we send the result back to the model for further thought. Once we get the final answer, the output is served to the user. Control flow in LLM systems are sets of steps before and or after an LLM call. Control flow steps are often called chains. Chains represent sequential or parallel steps that pass input to or process input from LLMs. These can be hard-coded, which provides high reliability and reproducibility. Alternatively, they can be LLM generated. If we want an LLM system to pick its own control flow, we are diving into the territory of agent-based systems. There's essentially a spectrum from strict processes to dynamic control flow, although terminology has evolved to the point where an agent can mean any control flow operations that operate within the context of an LLM application. Agents function on a spectrum of autonomy, from completely human-driven to entirely agent-driven. At the lower end of autonomy, humans write explicit code that decides the output of each step, which steps the agent is allowed to take, and decides what steps are available to take. Moving down the levels of autonomy, we see a chain-based execution. This is where an LLM generates multiple outputs for a step, but a human decides which steps to take. In a router architecture, the LLM generates the output and also decides which steps to take next. The human constrains the router-based execution by indicating which steps are available. In a fully autonomous system, an LLM provides the output, takes steps, and also determines which choices of steps are available. The level of autonomy you allow in your environment will depend on many things, including compliance, risk appetite, overly zealous CEOs trying to drive value, and so on. Let me elaborate on router systems. These represent the lowest level of agentic approach. The LLM selects a single step from the specified options, making them more restricted than fully autonomous agents. The trade off is that there is a higher degree of application reliability. There's at least some amount of determinism baked into the application because a developer has decided which next steps are possible or allowed. Fully autonomous agents, on the other hand, are long running agents with many available actions. They have complete freedom to select any subset of steps. This provides the highest risk but also maximum flexibility. Model Context Protocol, or MCP, is an open standard for AI systems to connect and communicate with external tools, data, and services. It was introduced by Anthropic in 2024 and acts as a standardized universal language for LLMs to fetch real time data, execute functions, and take actions. MCP is a client server architecture. An MCP host establishes connections to one or more MCP servers. The MCP host does this by creating one MCP client for each MCP server. Each MCP client maintains a dedicated one-to-one connection with its corresponding MCP server. The MCP server is the program that serves context data, regardless of where it runs. MCP servers expose three key types of data, or primitives. Tools, which are executable functions that API applications can invoke to perform actions, like file operations, API calls, and database queries. Resources, which are data sources that provide contextual information to AI applications, like file contents, database records, and API responses. And prompts, which are reusable templates that help structure interactions with language models, like system prompts and few-shot examples. Luckily, we don't have to build any of our agents, models, MCP clients, or tools from scratch. There are some extremely helpful frameworks out there that can help us navigate this massive ecosystem. LangChain is one of the most popular open source LLM application framework tools. It has a modular workflow and provides useful context helpers like prompt management tools. Llama Index is another framework that has a particularly strong data integration ecosystem. It integrates with over 300 different data sources. AutoGen is an agent framework developed by Microsoft that focuses on multi-agent workflows. Now let's dive into the LangChain framework, which is a powerful tool for building LLM applications. LangChain is an open source framework for building custom agents through chaining sequences of logic, reasoning, and tools. It's community driven with an extensive contributor base. The core platform of LangChain is a wide array of abstractions for integrating with the larger software ecosystem. It's basically a huge library of wrappers over key third-party functionality so that we can chain all of it together to form the complex interactions we need to make our ML systems work. There are abstractions for databases, for tools, and for models themselves. LangChain has integration packages as well that let you interoperate with proprietary models like those from OpenAI and Anthropic. LangChain also has community-supported integrations with third-party APIs. There's likely a LangChain component for almost anything you can think of integrating into your ML or LLM application. The key features of LangChain are quite comprehensive. The LLM interface allows you to programmatically query LLMs, whether open source or proprietary. Prompt templates are components that provide reusable prompt structures. Agents handle orchestration and decision making. The agent's functionality allows you to compose and customize existing chains for complex applications. Retrieval modules help you architect RAG systems and offer built-in semantic similarity and vector search capabilities. Memory support includes both simple short-term and complex long-term memory that you can integrate into your LLM applications. There are even callbacks and webhook components available to help you with event handling capabilities. LangGraph is an extension for building stateful LLM architectures with multiple actors and applications. Its features include a visual UI that models actions as nodes and edges in graphs. It provides persistence for short-term and long-term memory. LangGraph has built-in approval workflows for any human-in-the-loop functionality you're integrating, and also provides real-time visibility into agent execution. Here's an example of modeling agents and actions as nodes and directed edges in the LangGraph Studio UI. This is particularly helpful for debugging agentic runtimes and applications. Let me introduce you to a very recent development in the field, the Open Platform for Enterprise AI, or OPEA. The Open Platform for Enterprise AI is a community of open source AI practitioners and maintainers who are seeking to provide a higher degree of standardization for AI systems. Their goals are to create consistent language and practices across the industry, create reference architectures for AI systems, establish best practices and industry standards while they are still being developed, and foster community collaboration through an open contribution model. These kinds of standardization practices are going to be crucial for the health of the open source AI community and avoid further centralizing AI capabilities within cloud providers. Rather than let CSPs themselves dictate what best practices are, the community can contribute to defining these best practices and encourage CSPs to join along. I encourage anyone who's interested to get involved in OPIA or similar initiatives. It's an opportunity to help establish standards, contribute to reference architectures, and shape the future of enterprise AI infrastructure. It's also a great way to build your own expertise in this field and receive informal mentorship from the field's open source pioneers. Let's look at the current state of agents in production based on real world data. According to adoption statistics from a LangChain survey, approximately 50% of surveyed companies have agents in production, while about 80% of companies are actively developing agents with production plans. The most common use cases are quite interesting. Research and summarization is the most popular use case. Personal assistance and productivity tasks come next. Customer service is also common. Data enrichment and transformation is another popular application. Code generation accounts for only 35% of use cases, which is interesting given all the hype around it. Interactive gameplay rounds out the common use cases. Regarding agent permissions, we see some interesting patterns. 43.4% of companies use read, write, and delete permissions with human approval. 42.9% limit agents to read only permissions. Surprisingly, 13.3% allow read, write, and delete without approval, which represents high risk. For production controls, tracing and observability are considered most important. Guardrails, including small language models and NVIDIA NeMo, are also highly ranked. Offline and online evaluation round out the key production controls. The biggest barriers to deploying agents, broken down by company size, reveal that similarities exist across businesses. Performance quality is the top concern, no matter the size of the organization. Cost is a distant second concern. Safety concerns also factor into the limitations. This concludes our content for the semester. This field is rapidly evolving, making this an exciting time to build expertise in LLM ops and contribute to emerging standards and practices. I want to take a moment to thank you for spending your valuable time taking this course. I hope that you've come away from it with the confidence to continue your cloud computing learning journey, and I can't wait to see what you built.